Hello, class. Today we will start chapter 3 and we'll spend the majority of chapter 3 talking about acids and bases. There are two main classifications of acid and bases that we will discuss in this chapter: the Bronsted-Lowry and Lewis classifications of acids and bases. Bronsted-Lowry are the much more common types of acids and bases and are typically not referred to by their proper name. They're just called acids and bases. Lewis acids and bases are much more specific and they are not as common, so they will be referred to as Lewis acids or Lewis bases. Okay. Bronsted-Lowry acids are proton donors. Bronsted-Lowry bases are proton acceptors. From here on out, I'll simply be referring to Bronsted-Lowry class of compounds as just acids or bases, okay, not by their full name. So let's look at this classic example from general chemistry. When we look at the product side of the equation, we see that water has gained a proton and that HCl is now just the chloride ion, Cl negative, and has thus lost a proton. Thus, in this reaction, water is our base and HCl is our acid. Okay, so let's review quickly what exactly is a proton. Okay, you might remember a hydrogen atom is composed of one proton and one electron, right? It's the one element on the periodic table of elements. That means it's got one proton, one electron. Okay, when a proton is abstracted from a bond, the electron from the hydrogen atom that it initially had to make that bond stays behind. Okay, this is represented by drawing an H plus to indicate that the proton is a hydrogen atom without its electron. Okay, so that's why we get the H plus. The Bronsted-Lowry acid-base reaction scheme also gives names to the products formed from the acid-base reaction. The conjugate acid results when a base accepts a proton, and a conjugate base results when an acid gives up a proton. So let's go ahead and let's see if we can try this example together. Okay, again, we're going to look at the overall reaction that we have here before us. Then look at the products and see, okay, which one of our reactants gained a proton and which one of our reactants lost a proton in this reaction. Okay, when an acid loses a proton, it forms on the product side what is called the conjugate base, which has a lone pair of electrons that resulted from the loss of just that proton. The making and breaking of bonds involves electron movement. We use curved arrows once again to describe this flow of electron density. In an acid-base reactions, okay, electrons from a base take a proton from an acid. And we see that right here. The base, electrons from a base, usually a lone pair, take the proton from the acid. Okay. Now, the electrons that made the bonds between the hydrogen atom and the atom it was bonded to stay with the other atom. Okay. So those electrons that were part of that bond stay with the other atom. We use our curved arrows to show where those electrons are going. So consider a specific acid-base example, right? The base attacks the acid using a pair of electrons. The acid cannot lose its proton without the base taking it. All acid-base reactions occur in one continuous step. We call this a concerted reaction. The base takes the proton, and the electrons from the hydrogen bond to the atom it was attached to stay with the atom, which will become the conjugate base. Okay, the mechanism shows two arrows indicating that two pairs of electrons are moving simultaneously. All right, it's really important that both of those arrows are drawn at the same time. A multi-step reaction is shown here below, okay? So which steps below are proton transfers? Okay, if I look at my first step, which is right here, I see an O oxygen, a lone pair on oxygen, taking a proton from H3O plus, and then the electrons from the hydrogen-oxygen bond will stay on the oxygen. That is a proton transfer reaction. I'm transferring the proton from the protonated water to my compound. Here it's an alcohol, okay? In my second step, I only see one arrow. It looks like the electrons from this carbon-oxygen bond right here are being broken and just going with the oxygen. We're losing water. No protons are being transferred there, okay? In my last step, I see a hydrogen atom that is being abstracted by water once again, all right? It's a little tricky to see because this time our arrows are drawn a bit differently than we saw before, but if you look, you will see we've got the lone pair from the oxygen taking off this proton. The electrons between the carbon and the hydrogen are going to make a double bond, right? That's a little bit more of an advanced reaction that we'll see in Orgo 2, but this is still a proton transfer reaction. Lone pair taking a proton, the electrons between the hydrogen and the atom it was attached to stay behind.